Okay, we're back, and in this section we're talking about electric charge. But before we get into the topic of electric charge, we're going to talk about the structure of an atom, because it's the charged particles inside an atom that contain the charge that we'll be talking about in this section. So let's start by drawing a diagram of an atom. And what we'll do is draw the nucleus down here. We'll draw little particles here. I'm going to put a plus sign in a few particles here, and an N in a few particles. Okay, so we might have a clump of particles like that, and then put little negative signs around here, put a few particles, and then the outer edge, something like that. This is a typical diagram of an atom. You have this cluster of particles in the center called the nucleus, and it's made of protons and neutrons, and the protons are the one with the little plus signs there, and the neutrons are the ones with the N's. Okay, protons and neutrons make up the nucleus. And then electrons swarm around the outer edge. Now, a lot of people mentally picture the electrons as if they're traveling in an orbit around the nucleus, kind of like planets orbiting the sun. And people used to think that, but today we understand that they're not sitting there just moving around in circles like planets moving around a star. They fly all over the place. They jump around, and you can't actually pin them down. You can't actually say where they are at any given moment. What you can do is say where they are likely to be at any given moment. And the location of these electrons are described by equations involving probability and statistics. They have a certain percentage chance of being in a certain region at a given time. So they don't really orbit the nucleus, but they do exist in these little clouds of space around the nucleus, which we call orbitals. And then the other thing that you see in this picture is that the atom doesn't have a well-defined edge. That's why I've drawn it with a dotted line. A lot of times you can picture an atom as a little circle, or a little sphere rather. You might, for example, picture some salt as some atoms like this, bonded together in a pattern like this. And you picture sodium atoms and chlorine atoms bonded together. And just for conceptual purposes, it might make sense to think of the atoms as little tiny hard spheres packed together like that. But they aren't really tiny hard spheres. Like you see in this picture here, they don't have a well-defined edge, and that's because the electrons are on the periphery of the atom, and they don't have this perfect place that they sit all the time. So the atom is mostly empty space down inside here, all this stuff in between the nucleus and the electrons, and around the electrons is all empty space. The nucleus is packed down there in the middle, and then the electrons are swarming around it. And the other thing to note is that this picture is not to scale. The atom is very small, and the nucleus is very, very small. The nucleus compared to the atom is much smaller than is shown in this picture. If you were to picture, say, a large stadium or a large gymnasium or something like that, and maybe a little BB in the middle, the BB might be the nucleus, and then the whole stadium would be the atom. That would give you an idea of the relative size. And then the electrons are even smaller than the nucleus. So picture something the size of a gymnasium. That's an atom. If you magnified it to be the size of a gymnasium, then the nucleus would appear to be the size of maybe a BB, and then the atoms would be like little pieces of dust flying all around it. So the particles are very, very tiny compared to the atom, much smaller than are shown in this particular picture. And then the atom itself is still very, very small. It's just actually amazing to think about just how small they are. If you were to take 100 million atoms and line them up in a row, edge to edge, you would get a line of atoms about this long. Now, that's not exact. Different atoms are different sizes, but 100 million atoms lined up end to end, 100 million typical atoms would be about an inch long. So that's about approximately the size of a typical atom, 1/100 millionth of an inch. Another way to think about it is to think about this. Imagine one swallow of water. If you were to take a glass of water and just take a single swallow, all that water is made up of atoms. Water as you know, is what's sometimes referred to as H2O, and this H2 means there's two hydrogens, and the O means one oxygen. You get one oxygen atom and two hydrogen atoms stuck onto it like that. That's a water molecule. So in one water molecule, there are three atoms. And in one swallow of water, there are just hundreds of trillions of atoms. In fact, in one swallow of water, you would have so many atoms that if you were to expand each one to the size of a marble, you would have enough marbles to cover the United States several times. That's a lot. Picture the entire country covered with marbles from one side to the other and from top to bottom several times, several layers deep. That's how many atoms there are in one swallow of water. So when you look at a little glass of water and you think of all these tiny little particles, that can hopefully give you a mental picture of just how many there are down in there. So the point there is that atoms are very, very small, and there are a lot of them in just about anything that you deal with on the scale of objects that we deal with in everyday life.